Welcome. Let's take a look at finding the antiderivative of some basic integrands. Our first example is the antiderivative or the indefinite integral of 2 pi dx. Our differential here, x, tells us that the variable we're interested in integrating is x. So I see I have 2 pi here. So what I'm going to do is I'm going to bring that coefficient of 2 pi in front of my integral. And think of this instead as being 2 pi times the integral of 1 dx. Now, we call that the derivative with respect to x of x is equal to 1. So that means that the indefinite integral of 1 dx is going to be x plus our constant of integration. So this is going to be 2 pi times x plus our constant of integration. Our second example here involves trigonometric functions. Notice that we have cosecant times cotangent. And we need to rely on what we know about derivatives with respect to the cotangent and cosecant function. Now, recall that the derivative with respect to x of the cosecant function is negative cosecant x times cotangent of x. So that will imply that the indefinite integral of cosecant of x, cotangent of x, dx is going to be negative cosecant of x plus c. So this is going to be negative cosecant of x plus c. Make note that the derivative of the cosecant function has this negative sign, and where our original integrand did not have a negative sign, what we can do is we can simply think to ourselves, what if I were to divide both sides of this relationship by negative 1? And that negative 1 will pass through that derivative. And so we will end up with the derivative with respect to x of negative cosecant of x. And we'll end up with that positive value that we have in our integrand, or in the case without the negative sign. In this next example, we have the indefinite integral of 1 over u squared plus 1 du. So our variable in this case is going to be u. And what we need to rely on is that our knowledge of the derivative of the inverse tangent function, or arctangent, is 1 over 1 plus x squared. With that being the case, then the antiderivative of 1 over u squared plus 1, which of course we can rewrite as 1 over 1 plus u squared du, that antiderivative is going to be the inverse tangent or arctangent of u plus c, because of this relationship that is defined through the derivative. Our next example, we're looking for the indefinite integral of the square root of t cubed. The first thing we'll want to do here is take our integrand and rewrite it so that it is t to a power. So doing that, we will have the integral of t cubed to the 1/2 power dt. And then by properties of exponents, we multiply those two exponents and we get t to the 3/2 power as our integrand. So we have the indefinite integral of t to the 3/2 power dt. And so we're able to leverage the power rule in this case. So we'll be wanting to add 1 to this exponent. So our antiderivative or indefinite integral is t to the 3/2 plus 1 multiplied by 1 over 3/2 plus 1 plus c. So 3/2 plus 1 is 5/2. So we'll have t to the 5/2 power plus c. And then we have 1 divided by 5/2. So 1 divided by 5/2 is the same as 1 times 2/5. So, and 1 times 2/5 is simply 2/5. So this will be 2/5 times t to the 5/2 power plus c. Two more last examples. We have the indefinite integral of 2 to the x dx. So what we need to remember in this case is that the derivative of a base to the x power is the natural log of that base times b to the x power. So when I go to find my antiderivative here, I'm going to have 2 to the x power as the original function. Now when I take the derivative, I end up with a multiplication of the natural log of b. So when I want to find the antiderivative of b to the x dx, we're going to have to divide by 1 over the natural log of b times b to the x. Now, let's just verify that very quickly. What we want to do is to make sure that if I take the derivative of what I'm claiming to be this integral, that I end up with what I started with. That is, if I take the derivative of the natural log of b times b to the x, I will end up with b to the x. So derivative with respect to x of 1 over the natural log of b times b to the x. And that's going to be 1 over the natural log of b. That's a constant. And then now we focus on taking the derivative of that b to the x. And that's going to be the natural log of b times b to the x. And we can see that this natural log of b will divide out, giving us a 1. And we end up with b to the x. So in this example where I have 2 to the x, then my antiderivative is going to be 1 over the natural log of 2 times 2 to the x power. So over natural log of 2 plus c. And one last example. Let's go ahead and think about this carefully. I've got cosecant of y times cotangent y minus cosecant y. And we don't really have any properties for helping us deal with multiplication at this point in time. So let's go ahead and distribute this cosecant of y. And so we end up with cosecant of y, cotangent of y, minus cosecant squared of y dy. Now, we actually already found an antiderivative for cosecant y, for cosecant x times cotangent x, we saw that that is actually negative cosecant of x. So we'll go ahead and use that, except our variable this time is y. So we will have negative cosecant of y. And now we need to find the antiderivative of cosecant squared. And what I'm going to do here is I'm going to think of this as plus a negative cosecant squared of y. And then we're going to leverage what we know about the derivative of the cotangent function. That is, the derivative of cotangent is negative cosecant squared of y. So when I take the antiderivative of negative cosecant squared of y, I should end up with, let's make sure our variables match. When I take the antiderivative of negative cosecant squared of a variable, I should end up with cotangent of that same variable. So I've got negative cosecant squared of y. So my antiderivative here should be plus cotangent of y. And then I have plus c for my constant of integration. So notice that going through these examples, we're really leveraging what we already know about derivatives and basically reversing that process. In this case, we're in essence dealing with antiderivatives, and in the symbology here we have what's called an indefinite integral because there are no limits of integration. I hope you find this helpful.